three functional blocks of any networking device. So you have control plane, you have data plane, and you have management plane. So the control plane, as you see it, it's all about packets forwarding. Sorry, I think I skipped. Okay, so this talks about the data plane. So data plane is all about forwarding the packets. So this is very responsible for deciding what you want to do with the packet. You know, like the moment the packet comes in, you want to put it onto a particular path. You know, so if you look at any networking device, you'll have different interfaces connecting to them, right? Something will be in bringing the data in, something will be bringing the data out. Okay, and then this is where the packet scheduling happens. You know, like which packet gets what priority, because there will be a lot of flows maintained in the same device. So how would you actually do the scheduling of those packet flows? And of course, queuing comes in here. Let's say you're not able to really forward it as fast as you can. So obviously, you'll end up queuing these packets. Control plane. This is where this is the responsible. This is responsible for signaling, routing, and constructing the forwarding table. Signaling, as I explained before, it's more of setting up the sessions or exchanging some control information. You know, this is where the status will be exchanged between participating protocols, and ensure that it is all set for communication. Then routing. So routing is very important. It is basically to decide which path to choose. Any network device, the moment it gets a packet, it should decide how do I send it next. Okay, so routing, constructing the routing table itself is a very important area. It's a key challenge in designing a network operating system. How efficient are we going to construct the routing table? And third aspect is how do we construct the forwarding table? Okay. The slight difference here is in routing, you decide the path, which path you want to take in order to reach the destination. So the forwarding table is more like, what would be the next hop you want to take? Because once you identify for a particular flow, this is my next hop, for the subsequent packets in the same flow, you don't need to actually keep doing the table lookup in the routing. So rather, you can always look up the forwarding table, and all the packets destined to the particular destination can be immediately put up into the next hop using this forwarding table. Management plane. This is where you deal with the network management. Since they are all going to be distributed at different locations, you need a very stronger management framework, at least to get to know the status, or to control the devices, or even to provision the devices. Let's say you want to ensure that there are enough bandwidth for a particular video session or for an audio session, or you want to ensure that you want to restrict some of these users, so where you don't provide access to all the users into the network, or you want to ensure that there is enough QoS guaranteed. So in the management plane, you enforce certain policies, and there are certain parameters you set in so that you expect the network to behave in certain ways. So like how we did in the math notebook, where you have multiple users using the same notebook and different combinations. Similarly, here you have all those three planes could share the same processing units, or they could run on different processing units. Okay, so basically, if you want to provide a high capacity device, a router or a switch, then obviously you will end up having different processing units for different planes, because that makes it very faster. For example, the control plane would keep computing the routing tables and update the data plane, saying that, hey, this is how the topology keeps changing, and this is the modified or the up-to-date routing table, so that the data plane does not need to worry about how do I really compute these routing tables. Rather, they could just use these tables and straight away forward the packets that are arriving in. Okay. This is basically, for different, let's say if you are going to have different processing units. So certainly then you need to have some sort of powerful coordination mechanism between these processing units, because control plane, data plane, and management plane, all these three should work together. So certainly you need to employ inter-processor communication, which is basically, how all these three planes are going to communicate with each other. Message passing, this is between these units, like how they are going to synchronize, how they are going to exchange information between them. So for exchanging information between these processing units, you have various infrastructure supporting that. So one of them is message passing, and of course you need to have certain synchronization principles. Let's say the routing table itself, right? So there's a lot of changes happening in the network, and let's assume that the routing tables are going to undergo a lot of changes. How the data plane will quickly get to know this is the current table that I need to use. Okay, one such scenario. So number two would be, let's say you detected a security vulnerability. Let's say somebody else had broken into the network. You quickly wanted that session to be terminated. So suppose you got to know it at the control plane. So how do you ensure that this is communicated to both? So let's say you got to know it in management plane. How do you immediately communicate to the control plane as well as to the data plane, right? So you need to have very powerful synchronization mechanisms between them, so that all of them work together in unison to ensure that there is no issues of integrity, in the way how they function it. So some of the primitives what the OS should provide are queues, buffers, schedulers. As we have seen, queues are primarily meant to temporarily hold the incoming packets, and not just to temporarily hold them. Even they would actually decide how do we really prioritize this incoming traffic. How do we prioritize the flows? How do you do analysis such as the deep packet inspection? How do you really ensure that it's a very rogue traffic that is coming into it? Somebody is just pumping a lot of traffic into your server to really, deny the service that is offered by your server. So how do you really go about that? And of course, buffers, which is all about memory management. I mean, here the buffer management is slightly different from the operating system's buffer management. Okay, because in the operating system, at least each process will request for a particular amount of memory, and right up front, the process will be given or granted or will be denied based on the availability. However, in the network, it's quite difficult to predict the length of the flow. In other words, like at what rate these flows are going to come and how long it's going to come in that way. So in such cases, how do I really ensure that enough buffers are really reserved for a particular flow? So there are very interesting optimization problems, and how best the operating system is going to support that. And of course, schedulers. This is quite similar to the process scheduler, but here the whole concept is going to be based on how do you really match the incoming rate as well as the outgoing rate of packets, and how do you ensure that the schedulers are smarter enough to ensure that these packets are rightly placed in the right queues and they are forwarded further. So some of the algorithms or some of the primitives what the operating system is expected to provide. Let's say if it is going to be a router, so certainly there should be powerful routines or powerful structures should be made available for table lookups, because it's all about the destination route lookup, right? So the moment the packet comes in, you got to figure out to what destination it goes. Do I have a route for it? So I got to search for it. With the internet growing at exponential rate, so certainly these routing tables are really growing larger. Okay, so how faster you can look at the table? I mean, should you use hashing techniques, or should you use any tries or some special data structures? So how efficiently are going to organize them, or how distributed they are going to be? Because this routing table is going to put a lot of challenges both in terms of space as well as in terms of lookup table, right? Because they're going to be large, and with the IPv6 coming in, you have lots of address space, so certainly the destinations are going to be quite larger, and it's still, I would say, one of the hard research areas to even design the routing tables for IPv6. And of course, for switching, let's say if it is going to be a switch, it's going to immediately find the next hop and how sooner it's going to index the incoming packet, right? Let's say there are about 4, say ultimately whatever the amount of destinations you look at in a particular networking device, you will eventually have fewer outgoing interfaces, right? So among them only you are going to choose one of them, right? So that's where the indexing coming in. And nowadays the routers or the networks are going to offer lots of services, based on the user subscription, based on different types of applications that are running on the network. So certainly the packet classification is very important, and of course the pattern matching is one such technique that should be supported in the system, so that you are able to make use of that in order to do a lot of packet classification. And another key principle that we need to figure out is zero copy of packets. Let's say the packet comes in. So certainly it will be maintained in one buffer, right? Because you've got to take a decision. What do you do? What do you want to do with that packet? But if you really look at it, we all know that in a TCP/IP model, it's going to be 4 layers. But if it is going to be on a OSS stack, it's going to be 7 layers, right? How do you ensure that each layer gets access to this packet, but without you making a copy of it? If you really look at it inside the router or inside any network device, copying the packet is going to be the most expensive thing, because just now we have seen the packet is going to arrive at the line speed. Let's say if I'm connecting to a 100 Mbps link, then it's going to arrive at that particular rate. If it is going to be 1 Gbps, it's going to arrive at that particular rate. So the packets are going to flow, and particularly if you take video or some of the real-time traffic, it's just going to flow in certain rates. But at the same time, inside the design of the operating system, how do I ensure that these packets are rightly maintained, placed in certain buffers, so that the rest of the layers, instead of making a copy of these packets, they are still able to look at the packets. I can just quote one example where you can appreciate this concept and also the challenge involved in designing such a mechanism. Let's say the incoming packet arrives on an Ethernet. The outgoing the outgoing interface is going to be, let's say, token ring. Okay, just to illustrate it with 2 simple examples. The maximum transmission unit for each protocol is going to be different, right? So the frames, the moment they arrive in, for Ethernet, it will be, say, I think 1040 or, so it's going to be of that size. If it is token ring, it's going to be of a different size, right? So certainly at one case, you may have to fragment them and send it. At another case, you may have to assemble them together and send it. Let's say if the MTU of an incoming interface is going to be smaller, then you are going to assemble them. If you are going to assemble them into single large frame and send it out. If not, it is going to be, let's say you get a larger frame and your outgoing interface is going to be a smaller frames, you will have to fragment them. But all you need to do it inside the memory, right? How do you really make it as a zero copy? This is a very, very challenging thing. And in fact, there are a lot more ways to do this, okay? But how efficiently the operating system is going to provide that support to you, so that, the moment the packet comes in, without actually moving that data from one memory location to another memory location, can you actually achieve this? Okay, this, I would say, to me, is one of the most single design consideration. Can we really write an operating system, network operating system, that just guarantees a zero copy of packets? And then you need to provide support for protocols, right? So the way how protocols function, they are all perfect state machines. If you look at any protocol, the protocol will always have a start state, and based on some of the events that are happening, it will keep moving on to different states, and it will always remain at a particular state where it can wait for the next event to occur. Okay, and then it will have the final state, it will have some error state. So it's basically a perfectly, a prefixed, a predefined state machine. So that's why in networks, the peer-to-peer communication is going to happen without any difficulties, because both the participating parties will exactly know in which state they are in and in which state or which event they are expecting next so that they can advance their states, right? So how best the operating system is going to provide support for such state machines so that the protocol developers, they don't need to really worry too much about writing their own state machines. Rather, they define the state machine and leave it to the system so that the system actually, implements the protocols with a lot more ease.